Hello, everyone, and welcome. Today, we're going to extend our understanding of coordinate geometry into a new dimension. We'll be looking at three-dimensional coordinate geometry. By the end of this lesson, you will be able to derive the formula for the distance between 2 points in 3D space and apply it to solve problems. This is a powerful tool that builds directly on what you already know. Our main goals are to first understand where the 3D distance formula comes from, and second, to become comfortable using it. You'll recall that in 2 dimensions, we use Pythagoras' theorem to find the distance between 2 points. The great news is that the same fundamental idea applies in 3 dimensions. Let's explore the distance between 2 points in 3D. Imagine we have 2 points in space. Let's call them P1 and P2. These points have coordinates x1, y1, z1, and x2, y2, z2. The distance, d, between these 2 points is given by a formula that looks very similar to the 2D version. The formula is the square root of the sum of the squares of the differences in each coordinate. Notice we've simply added a term for the z-axis. But where does this formula come from? Let's prove it. It's a beautiful application of Pythagoras' theorem, twice. Let's walk through the proof. Consider our 2 points as being at opposite corners of a rectangular box or a cuboid. Here we have our cuboid. The point x1, y1, z1 is at one corner, and x2, y2, z2 is at the diagonally opposite corner. The distance d we want to find is the length of this main diagonal. To find d, we first need to find the length of the diagonal across the base of the cuboid. Let's call this length L. Look at the flat base of the box. It's a rectangle. The change in x is x2 minus x1, and the change in y is y2 minus y1. These form the 2 sides of a right-angled triangle on the base, with the diagonal L as the hypotenuse. Using Pythagoras' theorem in 2D on this base triangle, we can relate L to the sides. So L squared is equal to the square of the change in x plus the square of the change in y. This is just the standard 2D distance formula squared. Now take a moment to visualize a second right-angled triangle. This one is vertical. Its base is the diagonal L we just found. Its height is the change in the z direction, and its hypotenuse is d, the distance we're looking for. Here's our second triangle. The base is L, the height is the difference in the z coordinates, which is z2 minus z1, and the hypotenuse is our final distance d. We can apply Pythagoras' theorem again to this new triangle. This gives us d squared equals L squared plus the square of the change in z. We're almost there. We have an expression for d squared, and we already found an expression for L squared. Let's substitute our first result into our second one. We replace L squared with what it's equal to. So d squared equals the sum of the squares of the differences in x, y, and now z. The final step is to take the square root of both sides to solve for d. And there we have it. The distance d is the square root of the sum of the squared differences in each of the 3 coordinates. We've successfully derived the formula by applying Pythagoras' theorem twice. So we have now seen how the 3D distance formula is a natural extension of the 2D formula derived directly from Pythagoras' theorem. We are now ready to apply it. Now that we've derived the distance formula, let's put it into practice. In this section, our goal is to apply the 3D distance formula to find the distance between 2 specific points. We'll work through a concrete example to solidify our understanding. Let's find the distance between the point 1, 2, 3 and the point 3, minus 2, minus 4. First, let's write down our tool for the job, the distance formula. Here's the formula we just derived. Next, we need to label our points. It doesn't matter which one we call point 1 and which one we call point 2. The result will be the same. Let's designate 1, 2, 3 as our first point and 3 minus 2 minus 4 as our second point. Now, we substitute these values directly into the formula. Be very careful with the signs, especially with the negative numbers. Substituting the coordinates, we get the square root of 3 minus 1 squared plus minus 2 squared plus minus 4 minus 3 squared. Let's simplify the terms inside the parentheses first. This simplifies to the square root of 2 squared plus negative 4 squared plus negative 7 squared. Now we square each of those terms. Remember that squaring a negative number gives a positive result. So we have the square root of 4 plus 16 plus 49. Adding these numbers together gives us our final value under the square root. The sum is 69, so the exact distance is the square root of 69. For practical purposes, we can find a decimal approximation. The square root of 69 is approximately 8.31. So the distance between the 2 points is about 8.31 units. As you can see, once you have the formula, it's a matter of careful substitution and calculation. We have successfully used the formula to find the distance between 2 points in 3D space. All right, let's move on to our next key concept for today. We've talked about the distance between 2 points. Now let's talk about what's exactly in the middle of them. We're going to discuss the midpoint of a line segment in 3 dimensions. Our learning goals for this part are to understand the concept of a midpoint in 3D and to learn and apply the midpoint formula. So we'll define the midpoint and then learn the formula to calculate its coordinates. Just like the distance formula, the midpoint formula in 3D is a straightforward extension of what you already know from 2D. The midpoint is simply the average of the coordinates of the 2 endpoints. Think about it this way. To find the middle of 2 numbers, you add them together and divide by 2. We do the exact same thing for each coordinate. Given our 2 general points, x1, y1, z1, and x2, y2, z2, the midpoint, which we'll call M, has coordinates found by averaging the x's, averaging the y's, and averaging the z's. So the formula for the midpoint M is the sum of the x coordinates divided by 2, the sum of the y coordinates divided by 2, and the sum of the z coordinates divided by 2. Each component of the midpoint's coordinate is the average of the corresponding components of the endpoints. It's an intuitive and simple formula to remember and use. Let's now apply the midpoint formula we just learned. Our objective here is to use the formula to find the midpoint of a specific line segment. We'll go through a worked example to make sure we're comfortable with the calculation. Let's find the midpoint of the line segment connecting the points 3, 4, 8, and 5, 5, 5. First, let's recall the midpoint formula. The midpoint M is the average of each of the coordinates. Now we'll assign our coordinates and substitute them into the formula. We'll let our first point be 3, 4, 8, and our second point be 5, 5, 5. Plugging these values into our formula gives us the following expression for the midpoint M. So M has an x-coordinate of 3 plus 5 over 2, a y-coordinate of 4 plus 5 over 2, and a z-coordinate of 8 plus negative 5 over 2. Now we just need to perform the arithmetic for each coordinate. This simplifies to 8 over 2 for x, 9 over 2 for y, and 3 over 2 for z. Finally, we can write these as decimals or leave them as fractions. The coordinates of the midpoint are 4, 4.5, 1.5. This point is exactly halfway between our 2 original points. So we have successfully applied the midpoint formula. It's a straightforward process of averaging the x, y, and z coordinates separately. Now let's tackle a problem that requires us to use both of the concepts we've learned today. This is a great way to see how different formulas can work together. Our goal is to combine the midpoint and distance formulas to solve a more complex problem. The problem asks us to consider 2 points, A and B, with the given coordinates. We need to find the distance from the midpoint of the segment AB to the origin. When you see a problem like this, it's important to break it down into smaller, manageable steps. What do we need to find first? That's right. We first need to find the coordinates of the midpoint of AB. Let's call it M. Step 1 is to calculate the midpoint. Using the midpoint formula, we average the coordinates of A and B. So M equals 3 plus 2 over 2, minus 18 plus minus 2 over 2, and 8 plus 11 over 2. This simplifies to the point M with coordinates 2.5, minus 10, 9.5. Great. We've completed the first part of the problem. Now what's the second step? We need to find the distance from this midpoint, M, to the origin. Step 2 is to find the distance between M and the origin, which has coordinates 0, 0, 0. For this, we'll use our distance formula. The distance d is the square root of 2.5 minus 0 squared plus minus 10 minus 0 squared plus 9.5 minus 0 squared. This simplifies nicely to the square root of 2.5 squared plus negative 10 squared plus 9.5 squared. Calculating the squares, we get the square root of 6.25 plus 100 plus 90.25. Adding those up, we find the distance is the square root of 196.5, which is approximately 14.02 units. So by breaking the problem down, we were able to use both of our new formulas to find the solution. This example clearly shows how you can chain together different geometric formulas to solve multi-step problems. We found the midpoint first, then used that result to find a distance. Let's look at another type of problem, one where the distance is known, but part of the coordinate is not. This requires us to use our formulas in a slightly different way, involving algebra. Our objective is to set up and solve an equation for an unknown variable using the given distance. Here's the problem. We have a point whose coordinates are expressed in terms of a variable k. We are told its distance from the origin is 30, and we need to find the positive value of k. The key here is to translate the words into a mathematical equation using the distance formula. Our 2 points are pk, 2k, 5k, and the origin of 0, 0, 0. The distance d is 30. We'll set up the distance formula. We have 30 equals the square root of k minus 0 squared, plus 2k minus 0 squared, plus 5k minus 0 squared. Now, let's simplify the expression under the square root. This simplifies to 30 equals the square root of k squared plus 4k squared plus 25k squared. Be careful to square both the number and the variable in terms like 2k. We can combine the terms inside the square root. Adding them up, we get 30 equals the square root of 30k squared. How do we solve for k now? We need to get rid of the square root. We can do this by squaring both sides of the equation. Squaring both sides gives us 30 squared, which is 900 on the left and simply 30k squared on the right. Now it's a simple algebraic equation. To isolate k squared, we divide both sides by 30. 900 divided by 30 is 30, so k squared equals 30. The final step is to take the square root. Remember, this will give us two possible answers, a positive and a negative one. So k is equal to the positive or negative square root of 30. Let's check the question again. It asks for the positive value of k. Therefore, our final answer is k equals the square root of 30. This problem demonstrates how the distance formula can be used to create an equation that we can then solve algebraically. For our final example, let's apply what we've learned to a real-world scenario. This helps to see how abstract mathematical concepts can model physical situations. Our objective is to model a real-world problem using a 3D coordinate system and solve it with the distance formula. The problem describes a room with dimensions 3 by 4 by 5 meters. A fly starts in one corner and flies in a straight line to the diagonally opposite corner. We need to find the length of this flight path. The first step in a problem like this is to set up a coordinate system. It's easiest to place the starting corner at the origin. Let's model the room as a cuboid and place the starting corner at the origin with coordinates 0, 0, 0. The dimensions of the room, 3, 4, and 5 mm, will correspond to the x, y, and z coordinates of the furthest corner. So the diagonally opposite corner will have coordinates 3, 4, 5. The order doesn't matter for the final distance. The problem asks for the shortest distance the fly can travel. Since the fly can move through the air, the shortest path is a straight line connecting the two corners. This is exactly the main diagonal of our cuboid room. So we just need to find the distance between 0, 0, 0 and 3, 4, 5 using our distance formula. Plugging the values into the distance formula, we get the square root of 3 minus 0 squared plus 4 minus 0 squared plus 5 minus 0 squared. This simplifies to the square root of 3 squared plus 4 squared plus 5 squared. Calculating the squares gives us the square root of 9 plus 16 plus 25. Adding the numbers under the radical, we get the square root of 50. This is the exact distance in meters. We can simplify this radical. Since 50 is 25 times 2, we can write this as 5 times the square root of 2 meters. As a decimal, this is approximately 7.07 meters. This is the shortest path the fly can take. This problem is a perfect physical representation of the distance formula we proved at the very beginning of the lecture. All right, let's wrap up what we've covered today. We've taken our knowledge of geometry from a flat plane into three-dimensional space. Let's quickly summarize the key points. First, we saw how the distance formula in 3D is a natural extension of Pythagoras' theorem. We proved it by applying the theorem twice on a cuboid. We derived and used the 3D distance formula. Second, we learned the formula for the midpoint of a line segment in 3D, which is simply the average of the respective coordinates. We also learned and applied the 3D midpoint formula. Finally, we applied these two powerful formulas to solve a variety of problems, from direct calculations to multi-step problems, algebraic challenges, and even a real-world scenario. We saw how these formulas are used in practice. These concepts are fundamental building blocks for understanding vectors and other more advanced topics in three-dimensional space. Make sure to practice the exercises to become fluent with these calculations. Thank you for your attention.